Hi, my name is Avi Perlman, and this is Lab 4, a macroscopic view of DC and RC circuits. In this lab, we attempt to hone in on our knowledge of the loop rule, the node rule, Ohm's law, and capacitance in order to understand the behaviors of circuits, resistors, and capacitors. I utilize multimeters to measure the values of conventional current and potential differences and observe the behavior of resistors and capacitors in an effort to predict the behavior of circuits containing resistors in series and in parallel. The primary physics principles behind this lab are the node rule, which states that the sum of the current flowing in and out of a node must be equal, Kirchhoff's loop rule, which states that the sum of potential differences around a loop is equal to zero, Ohm's law, which states that the voltage drop across a resistor is proportional to the current flowing through it and its resistance, capacitance, and resistor equivalence. In the first part of this lab, I created a simple series circuit with two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters as shown in the diagram. Utilizing Ohm's law, I calculated the current through both ammeters to be 0.02 amps, which corresponds to the value read by the ammeters. Next, I replaced the bottom ammeter with a voltmeter, which read 3 volts, the potential difference across the batteries, while the remaining ammeter read 0 amps, as the circuit is open and there is no current flowing. Some key concepts from this simple series circuit are the fact that an ammeter reads the same value even when inserted backwards, and when a circuit is open, the loop rule does not apply because there isn't a closed loop. Next, I utilized a voltmeter to measure the potential differences around the circuit according to the schematic shown in the bottom left of the slide. I utilized the loop rule to verify that the sum of the potential differences around the circuit was zero. Here, it's important to note that the ammeter reading doesn't change when the voltmeter is attached because the voltmeter has infinite resistance, so the current remains the same. After that, I connected an ammeter in parallel with the 100 ohm resistor. Because the ammeter has zero resistance, all of the current flows through the ammeter in parallel with the 100 ohm resistor rather than that resistor taking the path of least resistance. Now the current only flows through the 47 ohm resistor. Utilizing Ohm's law, we can verify the ammeter readings of 0.06 amps. Utilizing the potential difference in current measurements that we previously found, we can find the resistance in each component of the circuit. We find that the 47 ohm resistor has a resistance of 47.95 ohms, the 100 ohm resistor has a resistance of 102.05 ohms, and the wire and ammeter have resistances of 0 ohms. In the second part of this experiment, I built an RC circuit with a 9 volt battery, a 10 ohm bulb, and a 200 millifarad capacitor in series. When I first connected these components, the bulb lit up and slowly dimmed as the capacitor charged. Next, I disconnected the battery and connected the capacitor directly to the bulb. Again, the bulb lit up and slowly dimmed as the capacitor discharged. Subsequently, I repeated steps 1 and 2 with a 20 ohm bulb. After that, I utilized the integrated timer in the FET to measure the charging and discharging times of the capacitor when connected to the 10 and 20 ohm bulbs. Here, it makes sense that the 20 ohm bulb takes longer to both charge and discharge than the 10 ohm bulb, as greater resistance means a slower flow of current. Finally, I set up a circuit with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb and charged the capacitor. I measured the voltage across the capacitor as it was discharging and plotted data for ln of delta V over delta V naught versus time. Utilizing the loop rule, Ohm's law, and capacitance, we can find that the slope of the linearized data is -1 over RC, and therefore we find that RC equals 6 seconds. If I were doing this lab in real life and used an actual ammeter, it would not have a resistance of 0 ohms, causing the current readings in the circuits to be lower than the values predicted using Ohm's law. If I used a real battery to charge a real capacitor with no resistor, the capacitor would be charged in a short period of time rather than instantly, as the real components all have some small amount of resistance.